Yeah, whenever you're ready.
Perfect. So it is my great pleasure to introduce Professor Hampei Sasahara from Tokyo Institute of Technology. So Professor Sasahara has been visiting us at UCSC for the last couple of months, and he'll be here until March 9th. So there's still time to initiate discussions and collaborations if this is interesting to you. So he got his PhD from Tokyo Institute of Technology. Then he did a postdoc at KTH in the group of Henrik Sandberg and Kali Johansson. Right? Yes. And yeah, since then he's been back at Tokyo Tech as an assistant professor, teaching courses in control theory and control theory applied to security problems. So it's my great pleasure to introduce you, and thank you for visiting us. So please take it away.
Thank you. Thank you for the kind introduction, and thank you for coming to my talk. So today, as shown by this title, I will talk about some security issues in control systems. But so I gave another talk in another security seminar, and the topic, most of the topic have overlapped with that one. And I can find many people have attended that seminar. So, but please understand it.
So after this, there's a quiz. If you don't get it after 2 presentations, they're out.
Thank you. Okay, so let me begin. So I will start from the general background, but in this talk, in the first half, I will talk about some review of existing techniques, and in particular, the most common technique used in control theory, so model-based anomaly detection, and other technical preliminary steps for the other topics. And in the later half, I will talk about my own work. Okay, so let me talk about background. So as you know, cybersecurity is a very important problem. So this is the report from McAfee, and it shows some estimated monetary loss due to cybercrime. And in 2020, it reaches $1 trillion US. And to make matter work, okay. So there is a rising trend. And this is not a problem only in the IT systems, but also in industrial control systems. And so I listed some of the incidents in industrial control systems, and all of them are very serious incidents. And in 2010, there was an incident in nuclear enrichment plant in Iran, and that's the most famous one caused by Stuxnet malware. But not only this incident, in 2015, there was an incident in Fabric in Ukraine, and recently in the USA, in the water treatment plant was attacked. So, and moreover, the recent development of digital transformation and industrial Internet of Things make threats more serious, as you can expect. So I think so this is the background, and let me describe the typical architecture of ICS, or Industrial Control System Network. So in ICS, usually there are two networks. First is information network, and the second is ICS network. And the ICS network is composed of the plant to be controlled and some field devices like sensor, actuator, and programming logic controller. And this is connected to more interpretable computer like human machine interface or emergency warning system. So this is a common architecture, and previously people believed that the ICS is safe. So it cannot be attacked because of these three reasons. First, it's intrusion-free because, as described by this figure, ICS network is isolated from the internet. And second, the fail-safe function would work even if something happened in the EWS. And finally, the unique OS prevents known vulnerabilities. So we have such a recognition. But in Stuxnet in 2010 was an evidence that this belief is completely wrong. And let me explain how Stuxnet worked and succeeded in the attack. In the Stuxnet, first, the Stuxnet tried to intrude the information network through phishing email. And after that, it infects some USB device in the computer. And an employee of the company brings the USB device to this ICS network. So it's physically disconnected, but it's connected through this USB device. And then the Stuxnet performed a preliminary attack to make EWS signal blind. And after that, this is actual attack. So perform some malicious operation in controller, and it leads to the critical failure. So this is the story of Stuxnet, and it is a clear evidence that those recognition are wrong. So this real incident shows the necessity of developing a new defense method for ICS. And also, I will give another example, recent one. So as I said, typical network is disconnected from the information network and ICS network, but recently in modern ICS, those networks are often connected through firewall. So our malware referred to as Toriton, it attacks the safety instrument system that governs remote access to EWS. So the Toriton succeeded in hijacking EWS. It is also a serious incident. And in the future, industrial Internet of Things will be implemented. And the wireless network replaces existing network in future, like the networks between the field devices will be wireless. So it means that enlargement of attack targets would happen. And so potential risk of undiscovered streets will be given because of the industrial Internet of Things. So those shows, again, those shows the necessity of developing a new security method for ICS. And the ultimate goal of ICS security research is, of course, we have already an IT security techniques, and it can protect the information network. But in addition to IT security, it's desirable to develop a new ICS security technique. And using both IT security techniques and ICS security techniques, we will get a more resilient system and achieving defense in depth. So this is the ultimate goal of ICS security research. So this is the general background of security issues in industrial control system. And I think you can understand the importance of security in ICS. So let me talk about more technical things. So first, as I said, I will give a review of model-based anomaly detection. This is the most common technique in control system, control theory. And this has a very long history, actually. So this is the history of control theory. So in 1960, the modern control theory was developed by Kalman. And just 10 years later of the development of modern control theory, observer design was developed. And observer design can be used not only for state estimation, but also for monitoring. So you can imagine that it can be used also for monitoring the system. It means the beginning, so this time is the beginning of model-based anomaly detection. So this is a very classic topic, and 50 years ago, but it's still being developed, and also, it's still being developed. But all of the techniques share the same core idea described by this figure. So this is the core idea. Okay, so we have a system to be protected with input and output, and we will create a model-based emulator here. So it will imitate the behavior of the system to be protected, and then we will compute some emulated output with the input signal, and just take the difference between the actual system output and the emulated output, which is called residual. And by applying some post-processing, we will decide if we should trigger an alarm or not. So a bunch of techniques have been proposed, but all of them share this same core idea. This is an important point. And let me give a more practical example with cloudable tank system. So this is quite often used in application. There are 4 tanks, and those are connected with 2 pumps. So we can get a math model by using mass balance and Bernoulli principle like this. You don't have to understand the math model, but what is important here is that we can get a math model, so we can apply the model-based anomaly detection to this system. And so to apply the model-based anomaly detection, we consider deploying sensors at tanks 1 and 2, and consider the switch scenario where the pump 1 is attacked, and the pump 1 flow exceeds the reference value. Okay, so and under this attack, the actual signal, actual output measured by these sensors at tanks 1 and 2 are given by this curve. On the other hand, the emulated output is given by this. So you can see that there are huge difference between this actual output and emulated output. So okay, we can conclude that there happens something, an anomaly happens. So in this case, okay, we can detect the attack. So this looks too simple, but this illustrates the core idea of model-based anomaly detection. And let me give a brief description of the technical detail of the residual generator design problem. So okay, so we have this frequency domain representation in the mathematical model. And so by applying a naive reconstruction, so if we use the system itself, the model itself, like GS, then this is the emulated output y hat. And the residual is given by this. So just the difference between the actual output and the emulated output. And then it should be 0 if nothing happens. But actually, the effectiveness of this naive approach is questionable in practice because there exists unknown initial state and model uncertainty. So the actual state is given by this under unknown initial state and model uncertainty. And then the residual signal is given by this. So you can find the 2 points here. The convergence rate of this residual signal exclusively depends on the eigenvalue of the original system matrix A. And also, influence of model uncertainty described by this term is not suppressed at all. So, those problem arises from control theoretical viewpoint. Those arise from open loop structure. So, to resolve this issue, we now consider introducing feedback structure into the model-based anomaly detection. And this term is a feedback structure. So I will skip the detail, but the previous studies show that a standard Lulenberg type observer works as this feedback gain. So this is the basic story of model-based anomaly detection and the most common technique in control theory. And here is a short summary of model-based anomaly detection. So the idea is that just to predict the benign output using the model of the system and take the difference between the actual signal and the prediction, which is called residual. And finally, it triggers an alarm if the residual is huge. And we need a mathematical input-output relation for model-based anomaly detection. And also, there is a tight relation between state observation and detection. So, okay. And finally, let me show another example with uncertainty. So we consider this quadruple system, but the model has some uncertainty here. Then, without feedback, with the naive approach, by using the naive approach, this is actual signal, but this is emulated signal. So you can find that it diverges, so it loses the stability. So, but on the other hand, the observer-based approach can track the actual signal. So you can find that with very small uncertainty, it doesn't work. The naive approach doesn't work. So we need to introduce a feedback structure. Okay. So it's too basic, maybe, but the fundamental of anything in security of control systems. So let me proceed a more modern topic called zero dynamics attacks. This is also review of existing work. It's not my work. Okay, the natural question should be, is it always possible to detect attacks by using model-based anomaly detection? And the answer is no, actually. When the attack is highly coordinated, it's called zero dynamics attack. Well, let me give an example. So in the previous case, we considered an attack only to the pump 1, but now consider both the pumps 1 and 2 are simultaneously attacked, and those attacks are coordinated. And by carefully choosing the coordinated signals, then the monitors physical values. So water levels of tanks 1 and 2 are very stable. So it's like the benign one. But the water levels of tanks 3 and 4 shows an overflow. So it means this attack is stealthy. We cannot detect the attack only by monitoring the tanks 1 and 2. And this is a core idea to generate such a coordinated attack. So regarding the pump 1, it makes it flow more than reference value. And then tanks 1, 2, and 4 water levels rise. And regarding pump 2, it makes its flow less than reference value. Then tanks 1, 2, and 3 water levels drop. And by carefully choosing the values, then the tanks 1 and 2 can be balanced. But the water level of tank 3 drop and that of tank 4 rise. So this is a core idea to generate such a stealthy attack. So from this example, we can get an observation that there is a need for handling such a coordinated attack in security context. Okay, and again, let me give some more technical explanation of this zero-dynamics attack. I think this is a control seminar, so you are familiar with this system description. It's a very fundamental state space representation. And the problem is to find another input U such that the output is 0. So for simplicity, we consider a very simple example here, where the input signal directly affects the output. In other words, there exists a field-through term. In this case, to create such a stealthy attack is very easy, actually, because the output is equal to 0 if and only if the input signal U is equal to minus x2. So in this case, the idea can be described by canceling the state signal by the input signal. So if there is a field-through term, this problem is very simple. Then the next question should be, what if no field-through term? So let me give another example, a bit more complicated example. There is no field-through term. The input affects the output through the state x2. And in this case, the idea is not only the canceling the state signal, but also considering the derivative of the output. So, okay, the output is equal to 0, then the derivative of the output is also equal to 0. And now the output signal is a second state. So its derivative is given by this state equation. So this means this equation holds. And from this equation, the input signal U is determined by this. And by canceling the derivative of this output signal, and you can easily confirm the converse also holds. Okay, so those simple examples, we can get a stealthy attack by canceling and considering the derivative. And also, this idea can be generalized to any system. And it's sufficient to find a suitable coordinate transformation. So the theory itself will be more complicated, of course, in the general case. So I don't explain it in more detail, but just for reference, I put only the result. So this theorem is a general result. So for any system, in this case, single system, we can consider a coordinate transformation, and we can get some stealthy attack by considering this signal. So what I want to say here is that we can get a complete characterization for such a stealthy attack. And note that this is a result for single system, but it's possible to generalize to multi-input, multi-output system. So, and also this is the reason why this is called zero dynamics attack will be explained. So we can define the notion of zero for multi-input, multi-output system by this definition. I don't explain it. But based on this definition, the stealthy attack, the obtained zero dynamics attack is given by or can be described by the zero defined by here. So it means that the zero dynamics attack or the stealthy attack is determined from the zero of the system. So this is why this is called zero dynamics attack. Okay, so this is a brief review of stealthy attack or zero dynamics attack. And in conclusion, systems property characterizes the existence of stealthy attacks. So control theory can be used for identifying some existence of serious attacks or analyzing some vulnerability in the system. So it can be applied to risk analysis So this is an example of this application. So in this paper, they defined the security index by the number of attack vectors necessary for generating zero dynamics attack, which is mathematically formalized this optimization problem. So the number of vectors, attack vectors, subject to zero dynamics. And in this figure, this is a complex network system. But if 3 attacks here are necessary for getting zero dynamics attack, then the security index of this system is given by 3. And in the example of quadrupole system, we can find that this input signal can be zero dynamics attack. So in this case, only 2 inputs are necessary. So the security index of this quadrupole system is 2. So from this analysis, we can get insight for defending the system. Like, okay, we need 4 more sensors, or we have to investment more to make it more resilient, or something like that. Okay, so this is the first half of this talk, and based on it, I want to talk about my own work. And first, I want to talk about some theoretical result about theoretical research. Okay, so as I explained, the model-based anomaly detection has been proposed, and not only the model-based anomaly detection, but a lot of automated intrusion detection tools have been developed in the general security context. So those help humans choose what defensive actions to take. So it's very helpful, but the problem is that it still requires huge effort. So humans have to make decisions based on the result of their intrusion detection tools. So to resolve their issue, autonomous cyber defense has been proposed. And it's defined as an agent that protects systems through high-stakes decisions without human authorization by using high-level countermeasures like not only detection, but also hardening, endpoint management, threat detection, or recovery. And actually, this is a recent, very hot topic. So you can find many recent papers published in a few years. So the objective of ACD is to make an autonomous decision without humans' effort. So the key techniques should be the reinforcement learning and control theory, because those are fields that handle such decisions autonomously or mathematically. And let me give a conceptual example of ACD applied to ICS. Now we consider a water distribution network here. This water distribution network is composed of the physical plant is composed of reservoir, pump, valve, tank, and external network. And the water level of the tank is monitored by an ICS network here. And in this ICS network, the appropriate control command is calculated by this PLC, and an on-off control signal is sent to pump and valve. And we have considered a switch scenario where the adversary intruded into somewhere in the ICS network. And now consider deploying an ACD agent here. And the ACD agent monitors the ICS network and also the physical process. So it can monitor the data, like, for example, packets in the ICS network, and logs in human machine interface in the ICS network, and physical quantities and water level in this case. And based on the monitored data, the ACD agent decides appropriate defensive actions, like to activate fail-safe function of the physical plant, or isolate components in the ICS network, or restore control variables in the controller. Those are just examples. So we can consider a more high-level or more abstract action. And also, the agent, it's expected that the agent can be designed based on the reinforcement learning using high-fidelity simulator. So this is just a conceptual example of ACD. And I think you now understand what is ACD, so autonomous cyber defense. But this has been recently just proposed. So it's still at the stage of formalizing the concept and taxonomy. So there remain a lot of challenges, of course. For example, in practical challenges like efficient handling of complexity in real-world systems. And also we need, of course, a high-fidelity simulator for GIM for each systems of interest. And as theoretical challenges, we need an appropriate algorithm, running algorithm, and reliable architecture of the agent. And also we need performance guarantee to use it or to convince the operator to use it. And actually, we are working with Professor Caldenas on the first 3 topics, but those are out of scope in this talk. And I will talk about the final one, performance guarantee. So I got a performance guarantee in a very ideal case. So let me give you the result. In particular, the research question considered in this talk is about the performance guarantee that can perfectly trained ACD agent beat rational adversary? In other words, or more specifically, the rational adversary should try to deceive ACD agent. Against such deceptions, if ACD agent has perfect knowledge of the environment, then can ACD agent make appropriate decisions, although the adversary tries to deceive the ACD agent? And the result is that, yes, the perfectly trained ACD agent can make appropriate decision in asymptotic sense. So this is the key term, in asymptotic sense, and I will explain it in more detail later. But this is a rough description of the result. Okay, let me go on to more technical detail. But before that, let me note that so this study has been accepted by IEEE Transactions Automatic Control very recently. So if you are interested, you can see this paper and you can find the early access. Okay, so we got that claim based on stochastic signaling game formulation. So first, this is a system to be protected and modeled by a finite malprecision process. And now consider the agent sender. So the sender represents the adversary, but the sender has a binary parameter theta, and theta b means it's benign, and theta m means it's malicious. So it corresponds to the cases where there doesn't exist the adversary, and there exists an adversary. And also we consider the agent receiver. So it's an ACD in our case. So the defender. And the defender takes a reaction by monitoring the state escape, but the receiver doesn't know the true parameter theta. So it means that the defender or ACD doesn't know the true scenario. It means whether the adversary exists or not, but knows the MDP and adversary's objective, which will be defined later. In other words, it has been already perfectly trained. And also the adversary knows everything. So we consider a very strong adversary. And for as a preliminary step, we put an assumption here. So mathematically it's described by this, but essentially it says that the system doesn't have any zero dynamics attacks. Because there exists zero dynamics attack here, then the attacker can make some attack without being detected. So just this assumption is made just for avoiding trivial discussion. And for that system, we will define the reasonable strategies taken by the adversary and their ACD. So we denote the strategy profile by this symbol S, and we define utilities. And in the reinforcement learning context, it's called reward and return. And we define instantaneous utilities here, and expected average utilities are given by this. And note that for the receiver or defender, this expected average utility is averaged over the belief owned by the receiver. So it means because the defender doesn't know the existence of the adversary. And we define the consistency of this belief. Or in other words, we suppose that the belief obeys the base rule. So the ACD makes decisions based on base rule. And we define the reasonable strategies taken by the adversary and the ACD. So mathematically described by this, but this is just a common notion in game theory and the Bayesian Nash equilibrium. So it is a widely used solution concept in game theory. And let me note that the BNE can be interpreted as a consequent when both both means the attacker and the defender perfectly learn the environment. And the only uncertain information is that the existence of the adversary. That's the only uncertainty. And in this case, what happens? So this is my main question. Okay, so let me analyze the Bayesian equilibrium. So we will analyze its asymptotic behavior. And first, we will analyze the belief's asymptotic behavior. So it will be very mathematical, but so please bear it. So first, this is a key lemma. The belief on the true type. So the existence of the adversary is a submartingale with respect to the filtration of the monitored state for any parameters. So this contains many mathematical terms, but you can understand it as the belief on the true type is monotonically non-decreasing in a stochastic sense. So based on this lemma, we can get some asymptotic behavior of the belief. So there exists a limit of the belief here. So we can guarantee the convergence of the belief under any solution concept or any reasonable strategies. And this is a proof sketch, yes. So this is a control seminar, so I think I can talk about some mathematics. So let me explain it. So essentially, lemma 1 is equivalent to, this submartingale requires two conditions, but essentially this requires this monotonically decreasing condition. And this, because this is a finite MDP, this can be decomposed into this summation form. And it's rewritten using traditional probability. And by applying the Jensen's inequality to this condition, then this inequality can be proven. And then we can get this lemma 1. And also theorem 1, this is a convergence result, is a direct conclusion based on Doo's convergence theorem. And this is analogy of convergence bounded monotone function. So this is a proof sketch. And there is a heuristic justification from information theoretic perspective of this result. So for the monitored state, this state series, the belief is specifically given by this form, and where this symbol S is defined by this quantity. And if strong law of large number can be applied, then it converges to the negative Kullback-Leibler divergence. So this means that the information available from the state is monotonically decreasing. And so because the information is monotonically decreasing, so the Bayesian update will converge. And it means the convergence of the proof of the belief. So this is a heuristic justification, but let me note that the strong law of large number can be applied only if the monitored state is IID. But in this case, the state observation state is not even Markov, so strong law of large number cannot be applied directly. So this is just a heuristic justification, but we can get such an information theoretic understanding. Okay, so based on this lemma, we can analyze adversary asymptotic behavior. So now we are interested in the situation where the defender possesses effective counteraction, because if the defender can't do anything, then the attacker can do anything. And we define this situation by defining the detection device utility. The utilities, as a pair of utilities, is said to be detection device utilities when the limit of the belief is less than 1, almost surely. So, and based on this detection device utilities, the adversary safe strategy should be behaving like a benign sender. So we define the asymptotically benign strategy. So this is mathematically defined by this, but it essentially means that the strategy of the adversary will be the same as the benign action and asymptotically. And based on this preparation, the main result here is that every Bayesian natural equilibrium is an asymptotically benign strategy. So this is the main result of this study. Okay, so this is another key lemma. So this lemma states that the state asymptotically loses this information about the type at any equilibrium. And this theorem is that message. So let assumption 1 hold, then every Bayesian natural equilibrium is an asymptotically benign strategy. And it can be proven by following these steps. So first, because the belief has a limit, according to theorem 1, the Bayesian update asymptotically stops. And in the second step, the state needs to lose information about the type from lemma 3 for the stop. And to decrease the information, the adversary needs to behave as a benign sender. This is a claim of theorem 2. And technically, this is an application of the generalized Fourier country second lemma. But anyway, okay, so this is the main result. Let me back a bit. So the main result is that every Bayesian Nash equilibrium is an asymptotically benign strategy, which means that the perfectly round LCD can make an appropriate decisions and asymptotically. Okay, let me give a simple numerical example. There are two state values, MDPs, and the adversary's action is also binary. And the adversary's objective is to keep state abnormal. But this is a normal state, and this is an abnormal state. And the defender's action is just to trigger an alarm or not alarm. So it's a detection problem. And this is a simulation result of one sample path. And this is the result of the belief. And this is the result of the adversary's action. The horizontal line is a time step. So you can find that the belief converges to a certain value after a finite time step. So this is the claim of theorem 1. And also, asymptotically, the adversary's action will be benign action. So it means the adversary stops the malicious action. So this shows asymptotic security given by theorem 2. So this numerical example shows justifies the obtained theoretical results. Okay, let me go.
The previous. So what did it mean? So what is the intuition behind this? So the belief means that the defender is just half of the belief says not under attack.
Okay, let me explain. The belief means that belief about the existence of the adversary.
Right.
So at the initial step, the defender doesn't believe.
There's an adversary.
Yeah, but at some point, so it oscillates, but at some time step, it reaches some threshold.
Is that the threshold 0.5 or not?
Not really, not actually 0.5. It looks about 0.5, but it doesn't have any meaning. But in this case, in this instance, it's just close to 0.5. But anyway, it has some threshold. And once the belief exceeds the threshold, then it keeps this value.
The adversary has to switch to stop attacking,
right.
Otherwise it's detected. Or...
Right, exactly. Yes. And the adversary tries to make the belief as low as possible. It's the adversary's strategy, but my theorem claims that it's impossible. It sometimes exceeds this threshold in a finite time step. Does it make sense? Okay, thank you. Okay, let me go on to the final topic. This is also a bit different from the previous one. It's more practical problem, and about adversarial attacks to data-driven control. So of course, there are a lot of data-driven methods and applied to games, generative AI, and also control systems like intelligent transportation system. And in control domain, a lot of line-based data-driven control methods have been proposed and applied to practical systems like nuclear plants and autonomous UAV and data center cooling. So, and we are interested in vulnerability of data perturbation in data-driven control. So it is well known that data-driven methods based on neural network are vulnerable to data perturbation. And this is a famous example in the image classification. So in the first example, okay, this is the clean data. And by adding very small perturbation to this image, then the neural network classification result will be given. Of course, this is funded, but the result will be given. But the human cannot see the difference between the perturbed data and the clean data. And this is the second example. So originally, it's a stop sign, but by adding very small perturbation, the max speed 100 kilometers per hour. So misclassification is led. And not only image classification, in speech recognition and reinforcement learning, the similar vulnerabilities have been found. So the natural question is that is the same vulnerability, are there same vulnerability in data-driven control? And this study raised this question. And specific target is direct data-driven control, which is recently proposed, so last year. So roughly, the direct data-driven controls will work as follows. So first, the control design phase, we will get data from data of the system, output of system, and input and output data. And by using this input and output data, we will design the controller without system identification, and then to implement the design controller to the system and make it closed-loop system. So it can be understood as a control design without system identification process. And now so in other words, it's an offline off policy one-shot learning method in the terms of reinforcement learning. And now we consider the three scenarios that the input and output data are perturbed by an adversary, slightly perturbed. And then the closed-loop system will compose of the system and the perturbed controller. And if the objective of the adversary is to make destabilize, to make the closed-loop system destabilize. And the question is it possible or not? Okay, and actually this has been also published in a conference, IEEE conference on digital control last year. And this is an example of a positive answer. It's yes. Okay, so for certain system, this is a clean data. And by applying the data-driven control for the clean data, then we can get the closed-loop system whose poles are illustrated by this. So all poles are inside the unit circle and very close to the origin, so this closed system is stable. And consider this adversarial perturbation, and the magnitude is 0.08, so very small. And it results in this part of the data. So you can see that those data are almost the same. But by using this part of the data, we can get this eigenvalues or part of the poles of the closed-loop systems. So you can find a pole outside the unit circle. And it means that the closed-loop system is destabilized. So it demonstrates that the data-driven method can be vulnerable against such a data perturbation. And in this talk, I will talk about the generation algorithm and dependent method and some numerical experiments. Okay. So this is a standard API control problem. I think you know control, some of control theory, so I can skip it. But this is very common control design problem. And the API control problem can be formulated as an optimization problem in this form. But in API control problem, it includes a model information. So originally, there is a need for system identification. And direct data-driven control is proposed to remove this need for system identification. And in the direct data-driven control, the setting is that the input and output data are available here, and the notations are given by this. So those data are given, but the system model is unknown. And the purpose of direct data-driven control is to solve this optimization problem without system identification. So and based on this setting, the idea of direct data-driven control is to represent the closed-loop matrix only with input-output data by introducing a new variable g. And the specific steps are by this, but what is important here is that the original optimization problem can be rewritten as the final one. So we can formulate the problem without the model information, and solving this optimization problem is called direct data-driven control. Visualization, it's not very important. I can skip it. So so this is the direct data-driven control. And next, I will talk about some existing adversarial attacks to neural network, not control. So so the scenario of the adversarial attacks to neural network is like this. So we have a test data X, and F is a trained neural network classifier with loss function L. And then the result is given by Y. So in the street scenario, the adversary put a very small noise to this test data or perturbation to the data. And then the product of data is given by x plus delta. So the result is given by f of x plus delta, and the label will be given by a wrong result, like given. Here, the adversary's objective is to find a small perturbation such that the result of this triangular network classifier are different. So small means that the norm of the perturbation is less than or equal to a given constant epsilon. And the most common approach or most common algorithm to generate the perturbation is referred to as fast gradient time method, FGSM. And the idea is to maximize the linear approximation of loss function. And it's analytically solved, and the result is given by this. And the meaning is that each element takes epsilon or minus epsilon, and the sign is the same as the corresponding element of the gradient. So this is the basic algorithm for adversarial attacks in the context of a neural network. So we consider applying this method to the directly driven control. Okay. So the street scenario considered in this directly driven control scenario is this. So the adversary can introduce some perturbation to input output data. And delta means the perturbation. And the adversary knows the system model and clean data and control design algorithm, and aims at destabilizing the closed system such that the closed loop matrix has eigenvalue outside the unit circle on the complex plane. So I don't have time, so let me skip some remarks. But okay. Okay, so this is idea or proposal. The proposed algorithm is referred to as directed gradient method, DGSM. And the idea is that, okay, originally FGSM makes a small perturbation that locally increases the loss function. So in FGSM, not increasing loss function, but shifting an eigenvalue in less stable direction. So I call it directed gradient time method. And this is the mathematical representation. But anyway, so the idea of DGSM is that originally, if the eigenvalue is here and the gradient is this direction, in this case, we make a perturbation to shift this eigenvalue to this direction. And if the gradient is this direction, then we take a negative sign to shift this eigenvalue to this direction, so to make it less stable. This is a fundamental idea of DGSM and the proposed algorithm. So, okay, I conducted some numerical experiments, and I will skip the detail of the setting, but this figure shows the effectiveness of the proposed method. So basically, this horizontal line shows the magnitude necessary, minimum magnitude of perturbation such that this destabilization occurs. So by comparing the random attack and DGSM, the required magnitude of the perturbation is very small, so much less than the random attack. So it shows effectiveness of the proposed method. This is what I want to deliver with this figure. And finally, this is also some logistic regression results, but I will skip also as well. Okay, thank you. So let me conclude my talk. So as I talked first, ICS security is a relatively new research field, and there is a rising trend of cybercrime, data transformation, IIoT, cloud computing are very important techniques, but makes or enlarges the attack surface. And many organizations and standards are being developed. And broad range of topics from classical approaches to modern ones, like model-based anomaly detection, zero-time attack analysis, model-based incident handling, and data-driven control. Okay, this is the conclusion, and thank you for your kind attention.
Okay, thank the speaker. Any questions? So I want to understand maybe a little bit more about the MDP formulation that you have in the middle, the one that I asked.
Okay.
So, I mean, that theorem of what is it exactly that it's showing? I want to understand what are the constraints in that game, or what are the assumptions, because it seems like a very general result.
Yeah.
That. So what is it that it? Well.
So okay, for that, the explicit assumption is just this one. No zero dynamics attacks or no hidden attacks. If the input signals or the attacks are different, then the probability distribution are also different. So if the same, if different actions lead to the same probability distribution, we cannot distinguish both actions. Okay, so it requires that it's possible to distinguish two actions from probability distribution. It may result in the sample, the same sample, but the probability distribution behind the sample are different. That's the only explicit requirement. But of course, there are implicit assumptions like the MVP is finite, and their type is binary or something like that.
Okay, yeah, I was just wondering also because what we're trying to do is to see, especially this autonomous cyber defense, if you're attacking the defender as well.
Yeah.
And in this case, it would be if the attacker can somehow lie, right?
Yes. So I think it corresponds to this assumption.
Right, but you're saying in there that, okay, yeah, you can. I mean, you have constraints on the line, right? Basically.
Right, exactly.
So
yes.
I wonder if maybe it can be modeled as a hybrid system. You normally is under this, and then under some situations it jumps to the lying probability or something like that. If I wonder if that can be modeled to see. Anyway. Okay.
PMBP is hybrid.
No, that probability distribution that not a high, well, I guess what do you call that when you have yeah, you just switch from one probability to another one. If you could report something different in the X, basically. So sometimes it is sampled with the P of X, and sometimes it is sampled by P prime.
Yeah, that's also another implicit assumption that the SED knows the true probability distribution or transfer probability. So if there is an error, the result will be different.
Right.
In the next slide, you are defining utilities. The belief is a number between 0 and 1.
Right.
So since you're having a game with opposite utilities for each of the players, right?
Yes.
Would you expect to have the expected reward of the first agent a 1 minus pi multiplying US, or is it like maybe somewhere?
That guy.
Yeah.
So this is not a symmetric game.
Okay.
I mean, the information possessed by the players are different. So the defender doesn't know the existence of the adversary, but the adversary knows her existence. So the adversary doesn't need to introduce the belief. So that's why it doesn't appear in this utility.
Oh, I see.
So this game is a kind of, the attacker tries to leverage their asymmetric information or asymmetric knowledge. And the question is, can the adversary fully leverage this their knowledge, the existence of the adversary, to deceive the defender? The answer is no.
But the attacker doesn't know if the defender has a belief of its presence, right?
In this case, it assumes that the adversary knows their belief of the defender.
Okay.
Yeah. So the adversary is very strong. She knows everything.
No more questions, so let's thank the speaker again. Thanks.
Thank you very much.
So yes, I was saying Hampei will stay with us one more month or a month and a couple of weeks. So do you want to reach out to him or collaborate, yeah, you still have time. So, yeah, thanks.
Yes, thank you. Okay, can I leave from this room? Great. Okay. Okay, thank you. Thank you for the online audience.